Hi everyone, in this video I will give you 3 proofs of chessboard problems in mathematics. So let's start with the first one on an 8x8 board. We have to prove that there exist 2 blocks on this board of this form. It could be rotated with the same sum. And all the numbers in this board are between 1 and 9. So if you want to try this yourself, then pause the video now because the solution is coming right now. Okay, let's first try to find how many unique positions of this block we can place onto the chessboard. So one position is, of course, this one. This one I'm drawing in pink. But we can move this another 1, 2, 3, 4, 5 times downwards. But we can also move this in 1, 2, 3, 4, 5 ways to the right. So that means that the amount of positions is equal to 5 times 5, which is 25. But we have to keep in mind that it might be rotated. So, and we have 4 possible ways to rotate. So we have to multiply by 4, which gives us 25 times 4, which is 100 positions. But every position has its own unique sum. So let's call that set A, which is a set with all these sums. So that is S1, S2, S3, and so on until S100. And let's now call the set B a set of all possible values that this sum can take. So B is all the possible values. But this is easy to check, because the minimal value will appear when we have all ones. So the value minimal is equal to 1 times 10, which is 10. Now the maximal value, let's call that value maximal, that is all 9s. So 9 times the amount of squares we got, and that is 10. So 9 times 10, which is 90. So that is our minimum and maximal value for the sum. So the set of all values is exactly 10, 11, 12, all the way until 90. But that means that the total amount of values is equal to 90 minus 10 plus 1, which is 81 total options. And now we are going to use something that we call in mathematics the Pigeonhole Principle. Pigeonhole Principle. Which just states that if you have, for example, 3 holes, but you have 4 pigeons, that means that in at least one hole there will be 2. For example, 1, 2, 3, and 4. So since every value Si is an element of B, we have in this case 100 pigeons, but 81 holes. So that means that there must exist an Si Sj with I not equal to j, such that Si is equal to Sj. So we have now proven mathematically that there exist 2 values in this set with exactly the same sum. Let's go to the second problem. For the second problem, we have to prove something about a 25 by 25 board. It is a board that is filled with all ones and minus ones. And we have to prove the following. Let AI be the product of the rows. So this is the product of row 1, and so on. And BI be the product of a column. So B1 is the product of column 1. And we have to prove that the sum of all AIs plus BIs is never equal to 0. So let's prove that by contradiction. So let's assume that the sum is equal to 0. Now, let X be the product of all the elements in this 25 by 25 board. So the product of all elements. So that is 1 or minus 1. But we can also write this as the product of all AIs from I equals 1 to 25. Because if we take the product of A1 to A25, we get the same total product. But we can do the same with the B's. BI from I is equal to 1 to 25. And let me introduce two new symbols. Let K be equal to the amount of negative ones in A1 to A25. So we just count how many times one of these values is equal to minus 1. And we call P the same value for B. The amount of minus ones in B1 to B25. So then we can do the following. Then this is equal to minus 1 to the P. And this one is equal to minus 1 to the K. And now let's multiply both these signs by minus 1 to the K. Then we get that minus 1 to the P plus K is equal to minus 1 to the 2K, which is minus 1 squared to the K, which is 1 to the K, which is 1. So then we know that this exponent has to be even, since minus 1 to the even number is the only possible way to get a 1. So P plus K is an element of 2n. But now let's use our assumption. We know that this sum is equal to the sum, first the AIs, from I is equal to 1 to 25, plus the sum of the BIs to 25. But now we know that this one we can write as 25 minus K times a 1 minus K times a minus 1. So we have this amount of 1s and K amount of minus 1s, so this will be the sum of all the AIs. And the same is true for the BIs. We will get 25 minus P 1s, since the rest are minus 1s, and then minus P, because we have P minus 1s. But this is equal to 50 minus 2k minus 2p, which is 2 times 25 minus p plus k. And by our assumption, this is equal to 0. But 2 is not equal to 0. So that means that p plus k must be equal to 25. But we knew that p plus k must be an even integer, and 25 is odd. So we have arrived at a contradiction. And that means our assumption is wrong, and in fact, this sum is not equal to 0. Let's go to the final problem. This is the third and the hardest problem of the 3. It is about a 200 times 200 board. And the question is as follows. The board is colored in red and in blue, and the number of blue cells minus the number of red cells is equal to 404. And we have to prove that there exists a square tile 2 by 2 that contains an odd number of blue cells or an odd number of red cells. So if you want to try this problem by yourself, start now because the solution is coming right now. Okay, we are going to prove this once again by contradiction. So let's assume all squares of this form are even. And with this I mean they contain an even number of red cells or an even number of blue cells. So that leaves us with two options, because without loss of generality it is either this one so these red and these blue, or it is this one, or it is just one colored. That are the only three options without loss of generality. So let's now look specifically at the first column. And I will call R is equal to the number of red cells in the first column. And B is equal to the number of blue cells in the first column. So notice it follows that R plus B must be equal to the length of the column, which is 200. But let me introduce some new symbols. Because these are the only options, we know that the second row has to be either exactly the same as the first row or exactly opposite of the first row. You can check this, because this has to be red-blue or blue-red, and then this opposite. And this logic yields for all squares, so we get that result. So let me call X as the amount of rows, or actually the amount of columns, that are the same as column 1. And let Y be the amount of columns that are opposite to C1. And once again, we know that X plus Y is just the total amount of columns is equal to 200. 400. So let's now use these four variables to solve this problem. Notice that the amount of blue cells minus the amount of red cells is equal to, and now we have to count carefully, the amount of blue cells is actually equal to the number of blue cells per column that is exactly the same as column 1, which happens x times, so x times the number of blue cells in this first column, plus r times y, because these red cells have become blue in the opposite way to column 1. So that are the number of blue cells. This value is equal to this, minus the number of red cells. And that is equal to the red times the columns identical to C1 plus the blue times the opposite one. And that is equal to 404. But we can factorize this, because this becomes b times x minus y minus r times x minus y. And this is equal to b minus r times x minus y. Now notice that from this equations, we get that b minus r is equal to 200 minus 2r, which is 2 times 100 minus r. And similarly, x minus y is equal to 200 minus 2y, which is 2 times 100 minus y. And if we plug in these quantities into this, then this becomes equal to 4 times 100 minus r times 100 minus y. And this must be equal to 404. But now we can divide both sides by 4. And then it follows that 100 minus r times 100 minus y is equal to 101. But notice that 101 is actually a prime. So its only divisors are 1 and 101. But also notice that both these factors are actually strictly less than 101. So the factorization 1 times 101 isn't possible. But that is the only possible way to factor 101. So we have arrived at a contradiction. So our assumption is wrong, and there has to be a block with an odd number of blue cells. So we are done. Now, if you like these problems and solutions, don't forget to like and subscribe, and see you on the next video.